that is so weird. Bring in like a big, thank you, John, and just smashing the cymbal. But you guys are all seated and quiet and listening.
Someone's whistling at us.
I heard that. I don't know who that was. I think jumped the gun. Anyway, so hey, welcome to the meeting. We're doing things as usual. We're doing something a little different. Which is to say, when Dr. Schaub comes up to give his presentation, he's just going to use his laptop and share his screen. Audio will continue to come through our presentation computer here in the meeting hall. So that's a little different, but we think it's also simpler as far as hooking things up. So we'll find out if anything goes wrong. So the first thing I will do before I introduce Barb is go ahead and kill that. Oh, look at all those people. And yeah, I might as well full screen that for when he shares his presentation. Okay, as usual, if you're new here, the restrooms are in the back hall all the way down. Thanks to the Coal Creek Canyon Parks and Rec for sponsoring us. And Barb, are you ready? She's going to come introduce Steve Schaub, who will be doing our talk.
Okay. So first, if you weren't here last time and you didn't get a July calendar, I'll hand these out. We haven't gotten the August one. It comes from Abrams Planetarium. So we'll have that for next time, or we'll have September for next time. So our next meeting will be September 6th. That's partly availability of the hall, but also we could have almost done August 16th. But the Park and Rec, our sponsor, and the school's PTO, it's kind of like PTA, are doing a movie night at the school, at the K through 8, which is now the Jefferson Academy, and they're showing Wild Robot. Now I went to their, I guess that was a week ago, they showed Hook, about Captain Hook, Peter Pan, and you sit out on the soccer field there and they've got a big screen. They pay $300 per movie, and the screen, you know, it's like an inflatable screen. So if it's windy, that would not be good, but I think they got anchors for it. But it was really fun. And so one of the other things we've talked to with the PTO, with Taya, who's the president, is doing some star parties, probably there at the soccer field at the school. And I would say, well, we would do pop-up star parties because you all know you can't really predict the weather. And so a day or two before, if you're on our email list, we'd let you know. And what I'd say, one thing, even though it's hot during the days, if we're there doing a star party, I bring a blanket, or I brought a jacket, and I was glad I did, because it does get cool, but it's really a very pleasant place to be there. And let's see. Oh, then also our sponsors, the Coal Creek Canyon Park and Rec, are doing the Mountain Fest. How many of you have been to the Mountain Fest before? Judy, Bob, yeah, a few people. Okay. And they usually have it here, and it's kind of a competition. And I don't know if they make you chop logs, but you've got to move them. They've got a whole little not obstacle course, but course where they do these different things. So that's going to be August 9th, also a Saturday from noon to 4, but they're going to have it at the school this time. And is there anyone who would volunteer to help there? I would. Stephen Langmuir and Bella helped last year, but they would like some volunteers. And you know, I don't think you'd have to volunteer more than an hour or so, but let me know. So I think that's my main comments there. And should I go ahead and introduce?
Sure.
So I am so honored, I think we are honored to have Hans Peter here tonight. We've talked about this, you know, Wayne and Marion and I. And sometimes Hans Peter for about a year. And he goes, oh, your astronomy, I don't know, you know, do people want to hear about, you know, aerospace engineering? And I said, yes, they do. You know, we had Angel Aboud Ahmad here from Colorado School of Mines a few months ago, and everyone really enjoyed that. And so we're really looking forward to this. And he's a local too. So he was raised in Switzerland. And I want to read this because I think this is interesting. And maybe you've seen this in the Mountain Messenger, but he was a fan of science fiction films that fostered his keen interest in aerospace engineering, from asteroid missions to satellite servicing and refueling, as well as dealing with space debris. And he's an internationally recognized expert on space. And you're the head of the Department of Aerospace at CU Boulder, you know, University of Colorado at Boulder. And I think you'll really enjoy this presentation. He's going to take us to asteroids and Mars and into space debris, right? Thank you.
Chairs. But thank you, Barbara, for the kind introduction. So yes, this talk doesn't quite go to Mars. You'll see Mars somewhere in there. That's another talk. You know, I've currently got about 18 doctoral students, another 3-4 research associates, army of undergraduates and master's students. So there's a ton of work. I get to present today a little bit of snippet of what we're doing, and hopefully a fun story. This is a talk I got to create a year ago when I got a Brower Award. It's one of the big technical awards in my field. It's an area I've been working on for about 25 years. I've probably got more publications in this area of charged astrodynamics and how to charge spacecraft and what we do with it than all the rest of the researchers combined. So it's one of the areas I'm quite known for, but it's also fun. This is a fun topic. Tractor beams, who doesn't love tractor beams, right? Star Trek, Star Wars. This is a great recruitment tool to get students to come to Colorado, you know. So we'll see. Barbara twisted my arm and said, I need to show this. My husband and Steve, who's in the background. Some pictures, and there's a little video. The last stop we did, I know with the internet it's a little bit stuttery, but we did get to go to Uganda and visit the silverbacks there. You saw briefly somebody down the lower right-hand side. That was really cool this summer. After this hike, I had kidney stones, 3 days getting out of Africa, bouncy roads. I do not recommend, but I did make it back within hours before I had to go to the emergency room and get morphine. So that was good. Good time. Amazing wildlife. I mean, it's hard to describe. Masai Mara, Northern Serengeti, all these areas. This is a leopard. She hauled up some antelope she caught and up in the tree, and she was basically just eating and sleeping for 2 days. Steve, this is one of Steve's pictures. You can see this is my pictures, and this is Steve. He's more of a professional photographer and artist. But just beautiful, beautiful landscapes. I know some of you here have been to Africa, and you know this one I like just because, you know, it gives a sense this is this Lion King like moment coming up, and that shadow is our car. So that thing really caught within feet of us. And if you look at the cars, there's no glass. It's just you and nature. And the saying is, as long as you keep your camera inside, we're fine. Now, look at Steve's camera. That was a hard problem. And Steve got promptly yelled at least 2-3 times for sticking things out of the car. But, you know, we survived. Barbara also asked me, so I am the department chair from the Smead Aerospace Engineering Sciences Department, the chance to maybe highlight, do a little outreach and say, what do we actually do? I'm always surprised in Colorado how few actually know what is happening in Boulder. And generally in the Front Range area, this is one of the highest concentrations, especially in the space industry, that you're going to find in this nation. And CU Boulder Aerospace, I mean, I know I'm the chair and professor there, but we really are one of the top schools in the world in what we're doing. Tons of faculty, 66, that's our tenure track, teaching faculty and research faculty. So a lot of prima donnas, eggheads, very opinionated people I get to lead, which is always exciting. Yes, thank you, Fred. You've been in academia, you know what that means. 1,800 students, about 600 of them are graduate. We have about 260 doctoral students just in our department. So our doctoral students exceed most other aerospace graduate programs, just the doctorals. It's an amazing amount of vibrant research and a lot of excitement that happens there. And it's fun to lead, but with this many students, any given day, somebody, I feel like strangling somebody every day. Because, why did you do that? But overall, the department is very research centric. So the first area, which is kind of a specialty, astrodynamics and satellite navigation, that's like GPS systems. Astrodynamics, this is the description of motion of spacecraft. How do you get from here to the moon, to Mars, different places, but also pointing spacecraft, rendezvous docking, that's my area. The craft you see on the left, that was actually built in Boulder. This is with the Emirates Mars mission, launched in summer 2020. Bad timing, but that's when the planets lined up. So, this was built here with the Emirates. They had tons of people that came over here and we went over there, and all the flight software, algorithms, all the brains of the computer were done in my lab with my graduate students. I had about 15 different graduate students who went through that. What's also fun is the autonomy group. In some places it's called control, but it's really, if you look at this craft, think of it darker. You might recognize it from the movie Twisters, the sequel that came out recently. If you've seen it, at some point they have these drones, they just throw it up and launch it. That's that aircraft or that design. It was actually built in our department because our department has a lot of storm chasers. Brian Arbro, Eric Drew, a bunch of people. This summer they were chasing hailstorms. Most of the time they're chasing tornadoes. And these aircraft have to be built to be very robust to take hail storms and fly, making their own decisions around the storm cells to do that. Why did the movie throw it up? Well, it's Hollywood. They wanted, how they launch it is a proprietary thing this research group does, and they didn't want to pay for it. So in the movie, they just throw it up and it flies. So how hard can it be? Easy. But that's one of our specialties. We also fly planes around Greenland, a lot of hard to access areas, The next one, bioastronautics. There's only a few schools in the world that have this, and it's all about sustaining life in space. So this is people looking at space suits, training astronauts, but also life sciences, medicines, bacterial infections, all the way down to the cellular level. How does it work? Thermal control is really hard to predict. But this is one of our strongest growing area because we're getting more and more people getting access to space. Pretty soon people will have kids, people have kidney stones in space. What do we do? I'm very sensitive to that. Fluid structures, that's kind of the classic engineering you will see, how to build structures and the fluids and fluid structures coupling. Some of the claim to fame for our department is we're doing probably some of the most complex numerical simulations of coupling. So, from big scale to small scale fluids, interactions, combustion, and the whole thing. And hypersonics, that's a huge thing these days. We've got a lot of hypersonics professors where the air chemistry changes as it flows over the stuff, and the shape changes because it's burning off part of the spacecraft. So that's all in that group. And then the last one, if you listen carefully, I said aerospace engineering sciences. A third of my faculty are actually scientists, and they're looking at Earth from space, looking at space from Earth and everything in between, a lot with these remote vehicles that you see, uncrewed vehicles, but also spacecraft. And so it's made this very nice synergistic relationship between the engineers and the scientists in my department that are looking at stuff. They apparently love cold places. They always go to Greenland or they spend winters. Some students are spending 12 months at McMurdoch. I'm assuming that professor, she does some good psychological tests with him first before she puts him down there. But that's a long time to be at McMurdoch. Anyway, so it's a really large, vibrant, exciting place to lead. And every professor kind of has their own research groups. We're almost like, you have to think of us almost like mini companies, right? We don't even get 12-month salary. We have to raise enough research and funds to cover our summers, cover everything for students, cover travel, cover everything. And so we're kind of running our own labs. Often we might collaborate. And these are some of the topics that are happening in my autonomous vehicle systems lab. So I do have one of the larger groups in the department. And top left, what you can see is a trusted autonomous flight mode. Basically, this is a symbol for neural networks. And what we're doing is using artificial intelligence to actually train these neural nets to fly satellites on their own. So as I keep explaining it to people, I'm not trying to figure out how I take a spacecraft and how do I make it turn left. I know how to do that. I've written a bloody textbook on this. I don't have to have AI rediscover what I already know. What I'm trying to decide is, should I turn left? Should I be pointing my panels at the sun and get power? Should I be pointing right and have my antenna download data to Boulder? Otherwise, my hard disk overfills and I can't do science. Should I be doing science? And if yet, what science? Should I be doing safety modes and so forth? So this is getting a huge amount of interest, and that's a whole other talk I could give. But I do a lot of stuff with artificial intelligence and spacecraft as well, and how to command them. To do that, we have this simulation software that we developed for the Mars mission, you can see in the middle. And this is called Basilisk. So a ton of research. How do we do these crazy, complicated numerical models for satellites that typically are one-offs? They build the shuttle, they make a model. They build, the Orion capsule, they make a model. And if the two dock, we need another model. And we're developing new mathematics to tie and glue all these things together in a very modular way. That's now being used by well over 100 groups. Research, big companies, small companies, and we're kind of the lead developer. This is also used for the Emirates Mars mission, as I explained. Currently, it's being used for the Emirates asteroid mission that they're going to. So we do a lot of mission support. Anything with rotation. So if you look at the top right up here, you can see close inspection right before rendezvous, docking, rotation. That's my lab. But today's talk is going to focus on this. And that's basically space weather interactions with the spacecraft. So I'm going to go a little bit through some physics. Promise, Barbara, I'm not going to throw any calculus at you or vector math or differential equations or plasma physics equations, but I'm going to talk about plasma physics in very rudimentary ways. Hopefully to get you a sense of excitement, why we're so excited about this technology, because I think it's super innovative. It's taking advantage of stuff that's been happening ever since we threw up the first satellite. But instead of finding ways to mitigate these effects of charging, and I'll talk about those, we're actually finding ways to exploit it. And we have some pretty exciting results what we can do with it. So today's talk, we'll start with basic physics. How does this work? Where are we going? And then I'm going to do a little bit through history. Who were the earliest pioneers looking at this? I'm not the first idiot who thought about this. There's other idiots prior to me who thought this is a good idea. And where are we now? Where have we been going? And then even the latest research, I only have one slide to give you an idea. This is where everything's exploding and getting fun and exciting. So, basics of space physics. Spacecraft are not flying in a pure vacuum. It's close, but it's not exactly right. You're flying always, if you heard about space weather, you hear about solar events, right? If you're all into astronomy, you've seen these events and so, the discharges. But even the sunlight hitting metal, Einstein studied this, it will eject electrons and things will charge. And so what typically happens in a plasma, it's something called a neutral plasma. That means there's equal number of positive and negative stuff. If there's more negative, they would push each other away, right? So it tends to be positive. But negative stuff is electrons, really tiny, small. Positive stuff tends to be like hydrogen atoms. That's the smallest positive ion you can have. Or helium ones or other ones. They're much, much bigger ones. So we're talking many thousands of times more massive. Because they have about the same energy, those electrons are just speeding back and forth much, much faster. The ions are really slow in comparison, which means statistically, you're much more likely to be hit by electrons. Now, this is ignoring sunlight right now. And what happens then is, happens when when some satellites go through the Earth's shadow. What happens is you start charging negatively. And then once you become more negative, you repel the other electrons, you attract more ions, and you get a new balance, what's called an equilibrium. But that's the balance that you achieve. This happens naturally all the time. The question is, how much do you charge? And if you look at the outer region, I'll talk about the zones. There's like the low Earth orbit where you're barely a few hundred kilometers above the surface. A lot of stuff flies there. But if you then you also have what's called the geosynchronous regime, which is about 42,000 kilometers out. That's where your orbit has 24 hours. So as the Earth rotates, that communication satellite is always over the same spot. If you have Dish Network or some of the satellite TV, that antenna just points at the sky and it doesn't have to scan satellites because it's all synchronous. In that area, the charging it measured could be 15, 20,000 volts. That sounds like a lot. But we're in Colorado. We experience this all the time. You're laughing, exactly. Right? Who here has not gone up to, a nice dry day, you go up, touch your door handle and get that zap? That's probably about 15, 20. We're talking about high potential, but very small current. That's why it doesn't hurt you. It just kind of gets your attention. Those are the potentials we're talking about with these satellites. So this is what happens naturally, and ignoring a lot of plasma physics. The idea now is, what if you add an electron gun? So this was the balance that naturally happens because electrons are going much faster than the ions. With an electron gun, I can get rid of these electrons. And so I can make myself less negative. I can even make myself positive if I put out enough current. And you achieve these new balances. So now I get control over how much I charge. So then we started to think, electrostatics, right? Again, Colorado, we're very familiar. We have dogs. I have very, very hairy dogs. I'm surprised you don't see any dog hair on me, but these are fresh clothes out of the laundry. That's electrostatics. A balloon, you charge it up. If you get really close, it starts to attract all of a sudden. And we want to do the same thing with spacecraft. So if you have spacecraft charged, and we're flying pretty close, we're not going hundreds or kilometers away, hundreds of meters, but we're going dozens of meters, worst case. These force fields drop off very quickly, so you have to be very close. But there are applications that I'll show you today, including space debris mitigation, that looks very exciting. But what can we do with this? So that was the concept. So now a little bit through history of charged spacecraft. What do people have been looking at? The earliest reference, and I know there's some, very experienced people here. If anybody has something that's earlier than this, please let me know. But this is the one I came across from Cover and a bunch of co-authors in 1966. This was the idea. I love this picture. This comes out of the patent. Looks like something out of a Jules Verne novel or something. But in the essence, what they wanted to do is the lower part is a metal grid that they want to charge to a potential. And then the upper part is a membrane that's also charged to a potential. And these two things were repelled. And they showed that, hey, actually, in the geosynchronous region again, 42,000 kilometers out, think communication satellites and direct TVs, there, the plasma is very amenable to this, and it only takes a few watts of power. We're talking like an LED bulb-like level of power to charge this whole thing up. And now this thing will inflate itself electrostatically. That was a 1966 patent. I don't think this has ever flown, but that was the earliest reference. Then charging was actually explored much more seriously in the 70s. There was the Left 2 mission, the ATS mission series, there was multiple, and the SCATHA mission. And they're flying in these communication orbits, geo, very far out from Earth. And they found weird events happening. All of a sudden, stuff stopped working. Like, now what? Everything was good yesterday. What happened? And then they decided to discover charging was a big issue, especially differential charging. If you talk to the charging community, the big thing they're worried about is, hey, this side is in the sun, it's charged to 100 volts. This side is in the shadow, it's charged to 5,000 volts. Well, if you have these two different levels, you can get arcing, right? It's like you touching the door handle, you've got that big differential and zap. And zapping, satellites don't like zapping. Electronics don't like zapping because you worry about all these discharges. It can actually literally burn holes in the circuits. It can do all kinds of bad things. So they were looking in the 70s, how do we mitigate that with active emission, which is kind of what we were talking about earlier. What if we added an electron gun or an ion emission, and we can now modulate the frequency? That's up. They did some charging experiments, but actually the outcome came, don't do active control. Let the charge happen, but avoid differential charge. I can't have one panel be 10 volts, one panel be 10,000 volts. That's what's difficult. But what if everything becomes 10,000 volts? That's not a problem. This happens on the Earth all the time. If you're on a ship, if you look at those Navy ships and have a helicopter come down, they often drop a cable first. They're actually grounding it because the chopper will be at some potential and the ship is at a different potential and you're equalizing it. But the whole ship actually has a ground level that floats and nothing, electronics don't care, and that's what these spacecraft do. So the design guidelines now are that those satellites have to have every outer surface electrically connected. So if something is charging up, everything charges up. And it's like a Faraday cage. You just build everything up or down. That is the principle we want to exploit. These satellites out there are already built like that. And if you go, for example, to Jupiter, talking to my JPL colleagues, they're like, man, HV Jupiter is such a crazy charging environment. You know, huge magnetic fields. They really have to deal with potentials, not three days a year, but all the time. They have very stringent requirements that everything is connected. So absolute charging is not dangerous. It's what we do all the time, even on the ground. It's the differential charging we want to avoid, right? And that's what they learned there. The Europeans have flown a cluster mission, which is interesting. They're one of the first ones I've seen to fly active charge control in space. Now, this is an artist rendering. It's beautiful, but completely wrong. You know, satellites are not flying, 30 meters apart. They're actually like 25 kilometers, so way, way further out. But that you wouldn't even see anything in this picture at that scale. So, but it is 4 satellites flying on this highly elliptic orbit through Earth's geomagnetic tail and getting measurements. There, they had to control the potential to near zero, and they have some experiments. But it was just done to bring your own potential to zero. It was never used to somehow act with forces between spacecraft, because they're flying so far apart, those force fields drop off super fast. Anyway, that was experience. But as a charging technology, this is not, all just out of crazy idea. This is being done and has been done. So the Middle Ages, this was like 60s, 70s. So then nothing much happened in the 90s. There was some good music in the 90s. There was something. But in about 2000s then, there was this project that started that was kind of interesting, that re-investigated this again. This was done by some colleagues of mine at Michigan Tech, Gordon Parker, Brad King, and a master student. Brad King is a propulsion expert. So if you look at electric propulsion, you're putting out ions. If you only spit out positive stuff, you make yourself super negative. And they have to always worry about charging. So he's very much an expert on that. Gordon was an expert on dynamics. And so they worked together on this NASA study to actually exploit. They looked at actual the data that showed you could charge to 15, 20 kilovolts at the right time. But what would happen if you would be flying 20 meters away? And turns out you can get millinewton levels of forces. Millinewton sounds really small, thousands of a newton. So Swiss by weight is always by chocolate bars, naturally, the classic thing, what is a Newton? 10 chocolate bars, 100-gram chocolate bars, that's 1 Newton. And I'm talking like 1,000 of 10 chocolate bars. That's a small force, but you're the biggest thing in town, because even sunlight hitting you, that might cause differential motion, is another about 100 times smaller than that. So we can do interesting things with these small forces, because you're just kind of floating along out there. And they found these solutions where all of a sudden they can attract and repel with these charges. And you can create these almost crystalline structures where things just kind of statically stayed in place if you placed them there. So that was exciting. Again, where does it happen? It's not low Earth orbit. The plasma is too cold, too dense. It's not the Van Allen belts. A lot of crazy physics happens in the Van Allen. That's where all the really bad radiation happens. You typically stay out of them. But this geo-regime, it's many Earth radii out. That's where your communication satellites are. So that's where we're working, not low Earth orbit. And these crystalline structures, we started to investigate in the lab. We found all kinds of interesting answers. The trick is, I'm going to use this one demo. I hope I don't see my video. There we go. You can see it. It's a pen, basically, right? What is this balance? If I'm holding a pen like this is a balanced pen. If I bump it slightly, it's just going to wiggle, and then with friction, it's going to settle again. This is also a balanced pen. But what's the difference here? I'm going to bounce this a little bit, of course it's going to go away. And so these things are essentially all perfect balances we found in the rotating orbital regime with all the other stuff, assuming little points, not spheres even, not finite structures, points that are charged. But it turns out they're all things like this. So that it's interesting that we have these balances, these equilibria, because if you put it perfectly, it takes no effort. But if it's imperfect, it takes effort to keep it there. This is nicer because this takes no effort, and if you balance it, it comes back by its own. I would love that, but that's not what nature gives us. So we've been exploring a lot of these and found very interesting shapes. This last one here, I'm going to show a 3D animation. You can see there's this pentagon, 5 rings on the outside, 3 on the middle. I mean, how cool is that? That with the mathematics of attraction and repulsion, electrostatic points, all of a sudden you get this almost like a communication dish and an antenna. So these are these virtual crystal-like structures that we're starting to discover and go, wow, this is cool. Many theses were written on this stuff. So then the idea at the beginning began, well, if we've got one shape and how to stabilize it, you know, if they have this, I have to think about how do I keep this here? Because real life isn't perfect. Real life is always messy. But the idea was, wouldn't it be cool if we have some structure and all of a sudden I have some dish and now I need to make it 10 times bigger or a different shape or change the focus, narrow focus, wide focus. People do this all the time for terrestrial planet finders, other kind of things. Some have adaptive optics as structures, but if it's a free-flying structure, it's like the VLA astronomy in New Mexico, if you're familiar with that. The movie Contact had all these radio dishes and you bring them in close, you get a finer, no, wider field of view. You bring them out narrower, I believe, and you know, you can do all that. You can do it on the ground because you're just, you know, moving things over. In space, that's much harder. If we could do it like this, there were several agencies that funded this, that would be exciting. But the mathematics gets crazy complicated, which is good for me. That means it's exciting. So how do we explore it? Just giving a little sense, you know, that's wonderful. What if I had 12 things, go magic? That's not where you start. We start with 2. Why not with 1? Well, with 1, I can charge myself all I want. Nothing's going to happen. I need another object to attract or repel myself off from. So 2 is the smallest charge thing we can do. And we looked at how to place them and do stuff. And that was fun. A lot of papers came from that. It's essentially like a 2-craft with a tether. But if you've seen tethered concepts in space, tethers can only provide tension. If they come too close, it can't compress, you know, it doesn't provide compressive forces. Well, with these electrostatic tethers, I can do line of sight tension or compression, actually. So similar mathematics, but as a big benefit in how we can apply it. So this was explored. In particular, this first concept, docking. Typically, if you come up to the space station, there's a big, you know, some loops. You eventually get in front of it, and then you slowly on a collision course, right? Because we want to do docking. Docking inherently is a collision. You have to make contact. So it's a gentle, careful collision. We found with electrostatics, I can actually look at the coupled charge orbital motion, and instead of just getting ahead and being on this collision course, I can actually gently fly above it. Then engage this tractor beam, which I call, you know, just electrostatic force field. If I could charge it and control both charges, we've shown this is actually completely, by controlling the separation distance, it completely stabilizes, and you could just pull them in this way. So from the orbit radial direction. The beauty there is at any point, I go, this is not a good approach. I can turn it off and you would just drift apart very safely. So you know, there's cool concepts what we could do here. Even including docking. This is some work where I don't have slides on this, but we do have a project, the phase 2 with an industry partner on electroadhesion. There's some companies, one of my former students, he's a founder of Starfish Space. They're flying a satellite right now, it has something like this on there, where you use electroadhesion to be able to dock. Electroadhesion is a concept used for micromanufacturing on the Earth as well, to pick things up electrostatically. And we're looking at space applications with the right materials. So a lot of cool stuff. There we had an NRO. I think, Leonard, do you have an NRO hat on right now? There we go. So this was a project where we're thinking, the free-flying stuff, crazy complicated math. If you're a controls person, this is a non-affine, non-linear control. And that's a lot of buzzwords. It's not trivial. What if we had actual physical? These blue lines now are physical tethers. I mean, tethers, I'm talking like, you know, almost, you know, dental floss, like very thin, very, very thin kit. That's all we need is the light forces. But if I charge everything to the same polarity, you create this internal repulsive force, and it would act a lot like a gas inflatable structures. You may have seen in videos, the space station, in fact, has a module right now up there. The Bigelows, they want to build space hotels, but it's an inflatable space structure that's been quite successful. CR Space, just outside of Boulder, they are wanting to build some of these. A lot of companies are building, you know, inflatable, gas inflatable structures. What do you think the big concern is with gas inflatable structures? the deflating part from the inflating part, right? Because we are flying full of space debris, yes, but also just micrometeorites and all kinds of stuff that can tear a little thing. So a lot of weight goes into these membranes. There's multiple membranes and how to catch this debris or just little dust particles that can hit you. But now I'm not making, this is not habitable because it's just free space. So don't put a hotel in here. But it's interesting, it's similar because I can get this electrostatic repulsion to inflate things. And we've done laboratory experiments actually doing stuff like this. And instead of these crazy complicated dynamics, the tethers just limit how far you can go and then give you passive stability. And so this was a fun project we got to play with. So you can see we're starting to get more and more complicated. And then the big event happened, and I'll get to that. So far, everything was finding out, what's this balance? And there's some cool stuff that we could find, but it's not stable, right? Anything off, but it exists, which is exciting. So how do we get stability? We started with two craft. The force field drops off with 1 over distance squared, just like the gravity force field. So then we have orbital, they're mathematically equivalent. So as soon as I know that, I have all this literature on orbits, why they are stable. If you're at the space station, it's on a circle, it will be on a circle, it will be on a circle 3 weeks from now, in the idealized math. The same happens with two spinning charged bodies. What was interesting in this particular paper is we're not flying, in a vacuum. These charged elements are flying in a plasma. That means the positive charged one here, in a plasma, you've got free electrons, free ions, positive, negative stuff, whizzing all over the place. If you become very negative, you're going to attract positive stuff. If you're very positive, you're going to attract negative stuff, electrons. And that's called the Debye sheath. It literally, statistically, you will have opposite charge accumulate around you, and that drastically affects the forces you can create. It's called Debye shielding. And so including the plasma effects, we can actually now predict up to what points this would remain stable. At some point, the plasma will make it go unstable. And anyway, this is like 12 months of my life. This is a cool result. You better like this plot. It was fun, but it was just 2. Then we went to 3 craft. Anybody here much into orbital mechanics at all? A little bit? No?
3-body problem.
It's a 2-body problem, right? Solved. Long time ago. Newton proved mathematically every orbit around, point mass, it's either a circle, it's an ellipse, it's a parabola, or it's a hyperbola. You may have heard of these terms, right? If we do astronomy, that's how we track what the orbits are of asteroids, or we have some extra solar stuff whizzing by, it's in a hyperbolic orbit through the solar system. Exciting things. If you go from 2 to 3, what are the possible orbits? 1, I wish. No. If you go to 3, there is no more analytic answers. This is where chaos. Poincaré, over 100 years ago, invented chaos theory. There's a whole mathematical thing around it. And it was based on this problem, going from 2 gravity objects to 3. But each gravity body has a fixed mass. We have something that's mathematically equivalent, but instead of fixed mass, I'm essentially with charge varying my mass. And instead of mass always being attractive, I can choose to make it repulsive. So after 100 years, we still have armies of PhD graduating with, hey, how do we take advantage of this and fly from Earth to the moon and doing that? In the electrostatics, this got a lot more complicated. But I had a PhD student who did, for the 3-body, find out how to stabilize it around with 3 and something that might scale. And we're like, man, we're onto something. We did find one. There's all these conditions, and we found some set of conditions that actually, if we have 3 satellites down the lower part, you can see they're in a line. They're all flying in a line, and you have to put them in there. But if you're slightly off, it stays stable. It's one of those things like this, without any feedback. And we're very excited, at least for implementation. We're excited about this. And then the world changed in astrodynamics. Then Iridium and Cosmos happened. So this is about 15-ish years ago. Remember Iridium Cosmos, Leonard? I'm sure, right? Iridium was an operating satellite. Cosmos was a Russian defunct satellite. It had expired its lifetime, so it was basically big debris. It wasn't even in the top 10 things of concern that day. There was many other things people were tracking, But, unlikely doesn't mean impossible. And this was a day when shit happened, literally. And these two things had just massive collision, created all this debris field. And overnight, the funding agencies all of a sudden go, oh, this Kessler guy that we've been hearing, Kessler syndrome and all these little math, yeah, it's cute and funny, but it hasn't really happened. It happened that day. And they paid attention. So this, in our research, actually meant a sharp left turn, because all of a sudden now we're like, so far I had people doing thesis, honor thesis, cool stuff. Nobody would fund me. I had some earlier things I tried, but they're like, yeah, well, maybe I'm not sure how this would be used. Here, we found a really interesting application where they're still funding us now for this. And that's what beat the rest part. So this is where we're really getting into the current stuff. Because also paying attention earlier, we started out with the spacecraft were point masses, little dots with charge, because the math was much easier. And now we're going to get a lot more complicated. So what's this application? I'll play a little video here and I'll pause it at places just to go through the concept. But this is what we call the geosynchronous large debris reorbiter. So as we go through this, we talked about any object in space. You're flying in a plasma, but also the sunlight. I'm always ignoring the sunlight just for simplicity. But basically you charge naturally. So that's your debris, and it's typically tumbling. And when I say tumbling at geo, we're talking school bus sized objects, and some of them have been measured going 40, 50, 60 degrees per second faster. So imagine a school bus rotating all the way around in 6 seconds, and you're supposed to fly up and go grab it. Good luck. That's going to be really dangerous, because if you snack it and you have more debris, that's not what we want, and it's going to be super expensive. So we're going to wait. Crap. Sorry. Bad professor. There we go. Okay. So as this plays, let's see. I was there. So we're going to fly up, and essentially our servicer will go up there, and we're going to now turn on an electron gun. And by doing this, several things are going to happen. Because I'm emitting negative charge, I'm going to have a surplus of positive charge on my craft. And you have to do this continuously. If you turn off that gun, it takes a fraction of a second and nature rebalances and you're back to the original balance. So with an electron gun, we're talking here 10 watts. Yeah, one of your deck LED lights, the brighter one, that's it. That's all it took. Maybe 20 kilovolts, very low current. And we aim that electric charge on the debris. I don't have to physically touch it. I'm just aiming it on it. I'm going to make it negative, myself positive. This creates an attractive force. So, okay, millinewton levels, again, small. We're not going to move things quickly, but I can move it without ever having to touch it. And of course, if you just create an attractive force, well, then you start pulling two things together. That's a bad thing again, because we're just going to maybe risk a collision. What we have to do here, the servicer does have to use some regular inertial propulsion to keep itself at a safe distance from it. But you can now gently tug the debris, tumbling, kicking and screaming, out to a disposal region, which is about 200 to 250 kilometers higher. That's kind of where they put their trash right now for the geo orbits. That was the concept we pitched. There was a big conference that NASA and DARPA organized, and then a small company made a business going. DARPA picked our solution, the program manager at the time, as the kind of the answer for geo, and things were cool. A year later, that program manager left DARPA, which is always horrible if you have your sponsor. That's your champion. Yeah, exactly, Leonard. Left. And this is only a year later. This is the fickleness of politics. We wrote a phase 2 proposal for this. And guess what the answer was in that phase 2 proposal? Like, hey, you did great on phase 1. This looks very exciting. Yeah, it's more than just this. It's like, well, nothing's collided lately. Clearly, it's not that big a problem. I'm like, I was not happy. But we've still received, we've continued to work on it because it's exciting. It's a fantastic dissertation. You know, my students are learning not just the engineering side, they're learning the space physics and how this all comes together. And it's a really complicated system. It makes an amazing topic and it's fun. They're making tractor beam stuff, you know. So we've continued this on. We think we could move things. You know, we're not throwing harpoons and nets sticky gum, balls, they're looking at all different concepts, or docking, again, 60 degrees per second and docking on that. L'Oreal's, this is a few years ago, they said, oh, we have an answer robotically, we can lock onto a tumbling object. Guess what the tumble rate was defined as? It must be less than, what do you think?
2 degrees.
2 degrees per second? Any other guess? It was less than 1 degree per second. Try to move your hand less than 1 degree, it takes 360, that's hard. That's what they considered a tumble. I'm like, you can't be ass bastard. That's not a tumble. I can't even see it move, because there's stuff really tumbling, big stuff. And we're talking, again, school bus is small these days. The new geosats is like a football field with a solar panel, massive, and it's rotating if it's out of control. How do we even approach this safely? We think we can. So at this point in our work, we're moving way beyond little point charges flying around. We're really bringing in all the physics. Now we have to have something charging us. We have to get to the full electromagnetics, electrostatics, this plasma physics. All this math has to satisfy it. How can things work? And there's one plot. I mean, the details aren't too important, but on the bottom, we have a 20 kilovolt gun. We're seeing what current should be set out. Because if you put out a lot of current, you charge yourself up. But as I'm charged, I'm pulling back, I become positive, I'm going to pull back those electrons. And less hits the target. So that's why you see on the servicer, as I put out more and more current, my potential goes up and up. Whoa. But the one on the servicer, it goes opposite, it would be negative, so it's minus the potential. It goes here, the maximum debris potential, and then it goes down again. So what's the best thing from a force? And a force is roughly proportional to the product of both potentials. And this was the plot. This got me very excited. So many things in orbits. You try to find these ways to get from Earth to Jupiter via Venus and to Earth flybys. These are all knife-edge problems mathematically. That means there exists a beautiful answer you're looking for. But if you wiggle to the left, you're screwed. If you wiggle to the right, you're completely screwed. You better be very, very close. And those are hard as hell to find. People spend months and years with code and trying to find these things. If that's what we have to control, good luck keeping this cost effective. Nobody wants to pay much to move space debris, right? This has to be cheap. This curve is very flat from a force perspective. That means if I don't understand the material properties just perfectly, or the space weather is a little different than I expected, it doesn't just collapse. It actually is quite robust, which was an exciting result. And Stanovsky is one of my plasma people that I worked with on this paper. And that was an exciting, we're really bringing the physics in now. The other problem we have is how do we even model numerically that I am charged and I'm tumbling and what happens at the other object? Because we're not dealing with points or spheres. We have three-dimensional structures. I know one spacecraft that was built like a sphere, but pretty much everything else. Now, even Sputnik was a sphere with antennas. It wasn't just a sphere, exactly. So, give you a sense of the problem. When we do attitude dynamics, I have to numerically integrate, solve these equations. And I have to, if I'm not being aggressive, 1 second time steps. That's the resolution I need. A Runge-Kutta, a fourth order, it's an integration type. It basically means I need to compute the force 4 times per second, per second I'm moving forwards in my simulation. Cool, how hard is that? Well, if I use finite elements, some of you, if you have engineering backgrounds, the way we solve these complex structures is you make little bitty triangles everywhere and then you can solve it. And there's code you can get and go, I will solve this for you and I will tell you your forces. It takes about 60 seconds. You go, okay, that's not too bad, 60 seconds. But if I want to simulate one orbit at GEO is synchronized with the Earth. So the Earth rotates around once per day. I have to simulate 1 day, 1 second at a time, and it takes 60 seconds per force, and I need 4 of them per second. It will literally take my computer about 1 year to solve this problem for 1 day. And we're going to have to run thousands of these simulations. I'm not going to be alive for the study today, right? So this is a fundamental limitation of how do we actually explore this now? Because I can't just go fly there and test it. I have to numerically model. As engineers, as scientists, we always have to have models around this, right? So there's different methods. So finite elements took about 60 seconds. You can have things that take about a second and called boundary element methods. That was the competing thing. And we use it as a stepping stone. And we came up with what's called the multisphere. You can see a lot of spheres. And this was a cool, beautiful answer because I can now compute forces and torques to within about 1% accuracy, which is plenty good for what I have to do, about 1,000,000 to 1,000,000,000 times faster than finite elements. So now I can do, thousands of simulations in 10 minutes and look at all the what ifs and have to do. And that was one of the Air Force projects that actually funded this. This was a 3-year effort to fully develop it. This last one, you see different size spheres and the distribution isn't even, which is good. That took a lot of work. It's called heterogeneous multisphere model. So now we can model any shape. So what does a student pick as a shape? So in the paper, you'll find the sea buffalo. And we go, what else, right? We can't pick an actual satellite because it might be export controlled or something else might be picky about this. So we pick the sea buffalo. And if you're ever curious what a heterogeneous multisphere model looks like, that's it. Pointy horns, sharp hoofs, all of this stuff. It's fun. This is Joe Hughes. This was really fun. Got to do that. But no, so now we're not just having point charges, we can have general shapes, and in my lifetime, I can compute the actual responses as I'm coming in, having coupled interactions, flying out again, and control the stuff. So besides just pulling it, there's another effect we got into, and that was electrostatic tumbling. And this means if we're not just a point or a sphere, you have, whoa, there we go. You have like 2 big panels. My arms are these panels. And if they have charge on there, if you know electrostatics, the closer 2 things get. If that dog hair gets very close to you and all of a sudden it sticks to you, or that balloon electrostatic sticks to you. Proximity matters. So if there's charge on my panels, and one of my panels is closer to you, this one is going to have a stronger force than this one. So all of a sudden, this one gets pulled stronger than this one, and that creates a torque. With torque, when we talked about objects spinning multiple tens of degrees per second or more, I can start to untumble it. So now I have to fly close. I have to carefully modulate this force field and turn it on and off or reverse polarity at the right times. But I can start to pull out the rotational energy. I do use fuel because I have to do station keeping to hold that in place. But without touching it, I can slow it down. And now if I have to actually go touch it and service it and fix something, I can do it in weeks. And that was exciting. So that was something we're looking at. This is more recent research because as you're flying 20 meters out and doing station keeping, you have to hold your position because you're actually literally pulling on each other. And so you need thrusters to hold that position. But if you have 3D effects coming where some panel is flying very close and then far away again, you get all these challenges. And if you're not careful, this can lead to collisions. And one of my students, he just defended, he was able to evaluate this all numerically and figure out how close can you fly with 3-dimensional shapes and still guarantee safety operations. So that's, things are getting a lot more complicated from the old days. Plus hardware, a lot of things for simulations. We're one of the few labs in the world who has this chamber dedicated for charging experiments. So thank you, Steve, for the picture. He came in and lit everything up cool, but this has an electron gun where we can irradiate stuff. You can see my student, Andrea Lopez, she's putting in a craft. I'll have other pictures showing stuff. There's an ion gun up here, lots of viewports, so we can see what's happening when we electrostatically inflate things. So a lot of the work we're doing isn't just numerical or with math, but it really is physical tests that we're doing, and we're trying to bring this all together. Sensing has been a big focus in this was the second Air Force science project I got. Touchless sensing. This is really important, even if you aren't doing these crazy Coulomb things, these electrostatic formations. If I'm flying up to like the lunar gateway, that's what they want to build around the moon, you're often approaching from the shadow. The sun will shadow you, and you'll be in the shadow of the gateway as you approach. And that means you have very different charging environment. We want to be able to measure the potential on the other object without touching it. So, because if you have to go up and touching it, you've already grounded yourself, and then why even measure? We're looking at multiple methods. One of them is actually looking at electrons coming out. So as you hit a metal has free-floating electrons in it. Think of it like a pond of water, lots of droplets. And you take a droplet and you throw it in that pond, you can actually have 2 droplets splash back, right? And so the same with electrostatics. With the one electron going into a metal, that electron will repel other electrons. And if the right speed, you can make it splash out electrons and do some weird stuff. So those electrons is something we can measure, But it turns out things get complicated. With three-dimensional shapes, those electrons can follow the force fields, and you can have focusing events like with the communication dish, or interior corners, and defocusing events like these sharp edges. So you have to be in the right place, but we can measure the potential quite accurately. And here's some experiments we were doing. This is the electron sensor we built, a commercial X-ray sensor that I'll talk about next, and the whole setup in there. The other method is X-ray. If you've heard of the word Bremsstrahlung, it's a German word, it means braking radiation. It has to do with any time a charged particle is accelerated. And so as we're slowing it down, coming to the target, we're going to decelerate it. You give off very weak, but you give off X-ray. We can measure all the energies of the X-ray, and the highest energy will be the difference in potentials between surface and beam. And that's another way we can touchlessly measure what is the potential. And as we try to control the potential, it's always much easier if you can measure what you're controlling. It's like your speedometer in the car. If you have no idea how fast you're driving, how does it know to speed up or speed down? And I need the same thing here. So this is going to enable a lot of things. What's cool with the X-ray, you see these spikes. These come out of the characteristic stuff. So when our electron beam is hitting this object, let's say it's hitting a solar panel and it hits glass, it'll give you a very distinct signature. It's just like a fingerprint. And I can not only tell what the potential is, I can also tell you that part is glass, this part is aluminum, that might be gold, this could be capped on. You know, we can do material identification touchlessly of a neighboring craft on top of potential. Then Northrop Grumman actually flew up a mission like that. The servicer had two satellites with, two solar panels flying out, and it wasn't tumbling, but I'm going to show you why this could be tumbling. They flew in, and this typical docking mission take a long time. If you watch the Dragon crew capsule approach the space station, you're like, oh, they're 10 meters out. Well, then go walk the dogs, do 2 minutes, come back, and now they're 5 meters out, right? And the speakers are all excited, but it's like molasses. It's very slow. So this is hugely accelerated. But what they did is Northrop Grumman flew up to an Intel satellite that only had one panel, and they were flying up to it, and then you stop 20 meters out, and you go, okay, let's turn on our next sensor. And that has like some other whiz bang stuff, and it goes good until about 5 meters. Then you go, okay, now I need to turn on my docking sensor. You make sure you stay there 10 minutes, 15 minutes, make sure everything's locked in, and then you can approach. So this could just take even 30 minutes. That's kind of what we're simulating. If this had happened when we had some space weather events happening, if we had charged to 2,500, 3,000 volts, and again, at GEO, we've gone up to 20,000 volts, 2,000 to 3,000 volts, there would have been enough charge on there that when I'm coming up with something that's symmetric, docking onto something that's not symmetric, you're going to start twisting it, torquing it. And at the end, you'd be docking on something going multiple degrees per second, way more than the 1 degree per second you talked about earlier. And there's actually paths. This is another paper they wrote on. If you understand these force fields and we can measure the charging before docking, I can find ways to do very subtle adjustments to my approach. And all of a sudden, I am not spinning up my target. And you've made your life so much easier, right? So a lot of applications. Now, I'm just about done. There's now the last 3-4 years, tons of work. I have no time to go through this, but I hope you get a sense of, this is exciting for us. Because beyond just a geosynchronous regime, people are very excited to go to cislunar. They want to land on the moon, do stuff on the moon. There's a little gateway they want to do. It's a bridge to maybe go to Mars. The whole cislunar region, and Space Force is also very excited about it. They found water in Shackleton's crater. They want to build up stuff. So around the moon, the plasma, the space weather is similar, where you have to worry about charging. And so but the physics, the space physics is quite different. So one of my students, Kaylee, she's really looking into that, and she'll be defending in about a year. This is just a collage of images, all the fun different things we're doing. Top left, photoelectron emission. This has to do with sunlight, looking at these electrons, where do they go? Because it comes off in all kinds of weird ways, and it impacts us. We're also looking at active charging experiments. In that chamber I showed you, we're not just putting an electron beam, we're actually now starting to charge objects on purpose, not just for sensing. We're doing electroadhesion. Lots of experiments, including that top right figure, ion wakes. We're creating wakes. In some cases, we're flying faster than the ions. So like a boat going through water, you get a wake behind it. we have the same happening with plasma, and it affects our sensing and the control, and we can now actually simulate in our chamber that. We're also looking at pulse beam versus continuous beam, and there's multiple balances. It's like having, instead of just being this and this, if the right conditions happen, this all of a sudden appears as a balance. And it just boggles your mind, but it's wicked cool math. I'd love to show you. But we're discovering it, and that means when we're controlling it, this makes life even more interesting, which means more PhDs will come from us. But we're really getting into the point now where I think with our experiments and what we're doing, the third Air Force contract right now is funding us an active charge control, and we're making good progress. But I think we're really getting to within a few years where we'd have everything we need to fly an actual experiment in space when we get opportunities. And so we'll see. It's been fun, the last 25 years to really explore some of these cool crystalline structures, but so many assumptions, to now stuff that we're putting together, validated in chambers, others have validated in different setups. It's really maturing and kind of become its own thing. So I hope you enjoyed this little history of charging in space and this electrifying research that we're doing there. I'm glad to take any questions that you might have about this. If you have any questions about Africa photos, please talk to my husband. Okay, thank you.
Questions?
Go ahead.
When you talk about docking like satellite to satellite.
Yes.
Is there any human interaction in that, or is that all computer control?
This is mostly uncrewed vehicles that I'm looking at. So this would probably be just, no human interactions. Orbital mechanics, as you know, it took a while to train humans, right? If you try to do docking, you have to slow down to speed up, and you speed up to slow down. And that just drove the first astronauts crazy, but they learned it. With charging, it gets even weirder, like that. I would expect this to be probably mostly automated at this point. And you have to respond very fast with some of this stuff. So it depends on the application. But I think for the most part, this will hope be all automated. Even the Dragon crew, the first few flights were crewed, and they had test pilots flying it. Today, nobody touches any controls. It does it all. I think this would be similar. Yeah. Any other questions?
Is the charge a positive and negative? Is that in constant flux? So a satellite,
Yeah.
flight, so it could be positive, it gets positive, it attracts negative,
Yes.
and then goes gradually negative and then starts to get so that. How quickly does that change? Like minute by minute or hours or years?
Yeah, it depends. So just to paraphrase the question is how much does the charge in the spacecraft change? It's not just a constant,
Yes.
because even in the geosynchronous regime, they put it up in a 24-hour clock, and over one day, even with the same space weather conditions, you will have different environmental conditions,
Yes.
and you will vary your charge. And people have studied this. There's a whole group of space weather people who look at that. And then, of course, you can have space weather change. We have solar flare events and other stuff, and things go up and down and storms, and it can all change. The regular charging, we're talking over a day. So it doesn't just change with seconds, but it could change within 20, 30 minutes.
Okay.
That's why this feedback is so important, because I can't just compute once, this is the right current and potential and do it, and then just set it and forget it. I really have to monitor, I have to measure what my response is. And so that's why the sensing of charge became so critical. Because now the way you get rid of ignorance is feedback, right? You try something that got me close, but I'm a little bit to the left. And now you adjust. And I can stabilize this on its own again. So yeah, that's definitely, it varies quite a bit. If you get storm events, there's some crazy stuff that can happen that is on the order of seconds, where all of a sudden stuff can snap, magnetic fields can whip out and come back again, and all these things can happen. And that could be much more difficult to track. In those conditions, I would say turn it off, hunker down, and just wait. Wait 2 hours. It's like a hailstorm happening. I'm not going to go, is this windshield really built for this? I'm going to find an overpass, park, wait, and then continue.
And is that always with the sun, or could it come from outside of our solar?
Well, no, it's mostly for the sun. The sun drives a lot of that. The stuff you have from the outside would be like cosmic radiation. It is giga electron volts, super high energy level, but it's like individual particles coming in. That's not going to cause significant charging. You worry for that from a human perspective, because that can really penetrate shielding and change your atom, your molecules in your body and your DNA. But from a spacecraft charging, cosmic radiation has really negligible impact. It's driven by the sun. Yeah. Yes.
So are you training AI to be able to respond to those conditions?
My students have thought about it. I've got these, let me call them factions. Not that they are war with each other, but, well, there's definitely a rivalry in my team, like, you're a part of the AI group, we're part of the tractor beam stuff. But there are students who are looking at détente and trying to figure out, can we use AI specifically to train this or help with the sensing? Because it can get very complicated. So if you have all this data set, could these networks train to identify these conditions faster?
That's a lot of data to feed through for like space weather.
It is. It is. It would be. And all the responses depend on material. That was the biggest problem. It's not like, oh, aluminum has this. Fine. But then aluminum in space is not the same aluminum as aluminum here. Things oxidize. Then they build up all these weird layers from the space environment. Has it been up there 5 years, 20 years? Some debris has been up there 40, 50 years now. Who knows what those material properties are? So we have to be very agile and be able to respond in a super robust way, That's kind of where we're looking at. And maybe that's where AI can help us. The beauty is I don't have to be super precise. I'm not trying to do precision landing right on this crater. I'm moving junk, and if it takes another week because I didn't have quite the right stuff dialed in, so what? As long as it's cheap, I don't have to unspin it. I never have to touch it. I can do it very cost effectively. So that's kind of the balance we're trying to figure out. I don't want to make this super expensive because that'll never fly. But AI might help. Yes, John.
Excuse me. Does any of this research, is any of it applicable to understanding variations in small asteroid orbits?
I'd say it's open. So what do you mean by small asteroid? How small are we talking about?
Oh, 100 meters to a kilometer across.
Yeah, again, if you're looking at charging, the only way charging would move me is if I have another charged object next to me, right? And an asteroid it'd have to be almost like a binary system where somehow that is pushing and pulling. And I don't think there's enough charging happening on it. Typically what I've seen with the asteroids is the major charging happens on the terminator where this, daytime shifts to nighttime. That's when you can see more of the charging. And one of my colleagues, Dan Shears, his student, Christine Hartzell, she was studying, is there enough charging there to actually maybe levitate dust? That was always some of the questions I'm looking at, But I don't think from a force perspective, because even 100 meters, if the other asteroid is 300 meters out, like these binary systems, that's a long way for electrostatics. And the force field, you double the distance, you get a quarter of the force. It drops out very quickly. The other way that you could move it is something charged on its own, flying through a magnetic field. You get the Lorentz force. And there are people who've been studying that for Earth satellites. But Earth's magnetic field is super weak. And so they're finding you don't need tens of kilovolts, you need tens of gigavolts. And you can have massive self-emission to that to work. And some people just ignore that number and go, well, it's been proven we can do it. Like, no, bullshit. Reject that paper. But I think with the asteroids, I'm not aware of any massive magnetic field that would have helped to maybe nudge those. The big thing I'm seeing with asteroids long-term is the York effect. I forget the 4 authors. Do you remember? I don't. Yeah, the York deals with basically sunlight hitting an asteroid, because asteroids are rarely perfectly symmetric. Something at this orientation has a little bit more exposed here, so more sunlight pressure is here than here. But the other part is it heats it up. And the other part is thermal re-radiation. So when this gets warmer, even when it rotates around, that radiation gives a very small force. And we're talking over thousands or millennia. Some of these asteroids are spinning up more and more. And that could cause all kinds of effects. Other orbital translation, that's just beyond my pay grade. I'd have to talk to my colleague Shears. He might have some ideas there, but I don't think electrostatics would be part of that at that point, just on the scale side.
How about spacecraft that could modify the asteroid orbit with electrostatics?
Has been looked at. There's the Europeans, Dario Izzo and Murdoch. She was looking at this. They had a concept, assuming the asteroid was perfectly metallic, so they could charge it up, because then the math worked. And it was still challenging, but that was something looked at. Could you do something like this as a tractor beam? It's essentially like the gravity tractor. They've talked about grabbing a smaller asteroid and bringing it closer. And this is easier to control. And how do you do that? This was an electrostatic idea they were playing with, but just the dimensions and numbers in the chart, and asteroids aren't metal spheres. They made it a little more challenging. Yeah. But no, asteroids are cool. We keep looking at that. JPL also, I was working with them. They had another concept where, like, close to the surface, you get these Debye sheaths, the plasma stuff that happens, and the potential fields drop off very quickly. Changes in potential field, the gradients of potential is the electric field. So if you charge, those sharp changes actually create very strong electric fields. And could you build a glider that would just literally electrostatically hover in those regimes? So no air, but you're kind of hovering in the, I don't know, it's just wicked fun thing to explore. Who cares if it's practical? It's fun math we're talking about here, But yeah, so that's been explored. And another colleague, Joseph Wang, he used to work with me at Virginia Tech. Now he's off in California school. He does really cool numerical models of that charging on an asteroid and what would happen off the surface. But that it would impact the orbit, I don't think it's strong enough. People have looked at space debris too. There's things called hammer objects. High area to mass ratio. Essentially, if you've seen those mylar heat, in the end, they wrap everything in this aluminum foil. They think some of this foil got ripped off. So if the foil's like this, it flies a while with the sunlight. Then for some reason, something changes, different area, different sunlight pressure. And these things just keep shifting all over the place. It's a sail, like a solar sail. And we looked at that with charging, and we found charging even there, it was super lightweight considering the area. Charging didn't impact the orbits much, but charging did impact the attitude. And so indirectly, if the flat plate is not flying like this, but all of a sudden with charging and the magnetic field, something happened where you're flying like this, now you have a very different sail orientation and you would have strong impacts. So there's a secondary impact from the tumbling that we could see, which pretty much made the whole bloody thing unobservable. I had to tell the sponsor, good luck, this will never work. But, sometimes they listen, sometimes they don't. But yeah, so I don't think that would be an impact, but, somebody might prove me wrong. But it's not my domain of expertise with asteroids. Yes, Barbara.
I have a question about your students and
Uh-oh.
AI.
Yes.
One of our people on Zoom here is dealing with massive numbers of papers that she's grading with her students. It isn't engineering,
Yes.
science. But do you have your students writing papers, and how can you tell, or do you, is it so advanced that you don't have to worry about them using AI or for their research?
Well, so just to paraphrase quickly, you're asking me with my doctoral students, and as we write paper, do I worry that my students are using AI?
Yeah, or even by, are
Oh.
you dealing with younger students?
Well, if you're dealing in classes, that's a different thing.
Yeah.
These days with AI, if your assignment is go home, think deeply, and give me a 1,000-word essay on the origins of Napoleon, that's not going to work. You're going to get back what ChatGPT or Gemini or some of those tools are, right? Because they do a great job, and that is used pervasively. We do worry about it, especially in coding. Freshman computing, we're having massive amounts of cheating. All of a sudden, people are doing horrible encoding, and magically they have very advanced coding techniques. And 30 people came up with the exact same answer. That was last May. They all got zeros.
Yeah.
We're not going to account for that.
How did you tell that they were?
They were
other than
identical.
that?
Those things were identical. The techniques were there. And it was clear to us this was not their worry. That was put turned in. So this is definitely a very big challenge. But on the use of AI, I mean, if your question is, do I worry about my students using AI to write papers? My worries are my students not using AI. Because AI is super helpful in writing technical papers. Let's say you're writing an introductions. These things can be highly technical. And in your mind, the story is perfect, right? You are so clear. You're telling exactly what you're doing. I can tell them, take your introduction, give it to AI, ask it to summarize your introduction. What are the top 5 points, right? And that's a very ethical way. It's another proofreader. but it's 2 a.m, right? These are grad students. They're always night owls. I'm asleep at 2 a.m. I'm asleep by 9 p.m. You know, so I'm not there, but they can use that. I've actually created a personal chat channel for my students where I put in all the rules I have about how a paper should be written. And this AI comes through and tells them, look, you're using first person terms here. You're not citing enough. Your figures aren't following these formats. You know, very basic stuff. But that saves me tons of time. What it doesn't tell them is, hey, you're using the wrong physics model. It's not that smart, not even close. And the same in the mathematics. So we do all of that. But the AIs, I think, have become very helpful. We're all using spell checkers. Good grief, I'd be screwed if I didn't have spell checker or grammar checker. But this is a more advanced version that you can take this and say, hey, look, check my, you know, we've all had texts where we have the repeated, and good luck catching that. Well, it's going to catch it very quickly, or it can tell it, look, you were doing this, but you're not citing any of these parts, or other things that you might oversee. So I think it's super important that we hold students accountable for, you know, we need to be held accountable as professors as well, that we're testing them in a way that's truly testing the student what they know, not what AI knows. Because to use AI, you first have to earn the right to those keys. To use that tool, you have to learn the fundamentals. Same with spelling. We all learn basic spelling, but I very much appreciate spell checkers. They should learn basic physics, basic logic, basic stuff, and then we use it. But we have to learn how to use it ethically and properly, you know, not just trust the first answer. How do you know it's right? If you don't understand the fundamentals, you're going to be in a lot of trouble. Because it can be 99% there, but that 1% will still kill you in an aerospace system. You know, that plane's not going to land. So I think that's the struggle we have right now is I want my students to graduate learning how to use these advanced tools. It's really helpful. You know, in my field, we're programming not just in one language, we have 5, 6 languages. 2 or 3 I'm using all the time, but all of a sudden I have to use something called YAML. How often do I do that? Well, I can go to Google, I can pick up a book and read 600 pages and figure out what to do, or I ask ChatGPT and it goes, oh, here's some script. I'm going, oh, explain to me what you're doing. And it does an amazing job explaining what that is. And then I ask for, what's your source? And it tells me the websites and I can go look at it if I'm not quite sure this is the right thing, you know? So there's ways to use these tools, and I really want my students to learn to use it. You know, the problems we're solving are hard enough naturally. So for the researchers, it's different. For students just going through the fundamentals, that's the big challenge we have right now, because AI is getting good enough to answer a lot of these basic questions. So we have to think more about directly proctored exams. You know, you don't have computer use. That's all I teach. That exam is a blank sheet of paper. I give you the equation sheet. I give it to you 2 weeks or more in advance, but it's a blank sheet of paper, basic problems. Can you solve this? And let me tell you, it is very evident who knows what they're doing and who's not, you know. You want the homework to get 100, 100, 100, and then get a 30 out of 100 on the exam. You know, the story tells itself. And that happens even in graduate courses. So yeah, it's an interesting challenge we're dealing with in education. I think AI is an amazing tool used in lots of ways, but we're still very much figuring out how to use it well. And I want my students to graduate because it's a tool they should know about and how to do this, you know, just like using Google as an internet search. Few students go to the library now because I don't, you know, you search up topics and you can find the papers and read this stuff. So, yep, I know, Steve is giving me the time's up.
Simple question.
Any other question? Anybody on Google, on Zoom? Any Zoomers have any questions? You'll have to unmute yourself.
Yeah, thanks.
How do you measure distances without affecting choices?
How do I measure distances to the other spacecraft?
Yes, sir.
Yeah, so there's different techniques. People use visual sensors. If I know something about the shape, I can track stuff. You can also use what's called LiDAR, very similar to what your Tesla might have or other cars, the self-driving, adaptive driving, they have all these sensors going out and measuring stuff. Those technologies are used a lot actually in space as well. So as things are coming in, even to the space station, they have all the different sensors happening.
Okay.
Yep, so that's there already.
I
Yes.
have a question. I'm in Zoom.
Please.
how would you use supercomputers in the work you're doing? Obviously, I think you probably could, but have you ever asked any of the organizations that have supercomputers to give you some time on them?
Well, for the charging work that you've seen, I haven't had to use supercomputers. Our move to coming up with these multi-sphere models saved us from that. And we found better ways to approximate these forces to get there. The work with AI can take massive amounts of data, and some of these things take a week to crunch. CU has a supercomputing cluster that we have access to, and so far it's been okay. But we're getting into, of course, as soon as you can solve one problem, you're trying something 10 times harder. And that's kind of what one of my students, she's doing. And so we might try faster computers, supercomputers in the future. But so far, I've been fortunate enough to have access to CU's big computing cluster. And that has done the work within a few days. And that was good enough.
Great.
Thanks.
Anyone else? Well, let's say thanks. So we'll switch over now. Leonard will give his presentation. John Asselos is keeping an eye on the sky to see whether he wants to set up his telescope. Clouds are kind of iffy, but we'll see. So stay tuned and we'll let you know. All right. Let's see if I can get this back. All right.
It's gonna be quick because I forgot my glasses.
Yeah, I'm gonna grab that chair and pull it over.
I want to tell you about what's going on. That's very exciting. HP has done some incredible work. The orbital debris problem is really ominous. But there's a lot of other things going on at NASA world, which is like going out of business. That's one probable outcome of the last few months. We got the Trump administration really putting the squeeze on NASA and other agencies in science that are going to be really telling here. I'm not sure where it's going to go, but I'm just saying, watch the skies. We had a NASA administrator that Trump actually gave a go-ahead to. Are we okay?
Yeah, hold on one second.
Okay.
I forgot to share screen.
Oh, God. Wait, sharing screen.
Yeah, let me get this guy off of here. Bring him down to here. Oh, come on. Let's see.
Right, I'm
All right.
quiet now.
All right, so let me get this back up there.
This is clever.
This is why I can sit here and look at the
Oh.
screen behind me.
Well, we had, Trump got a guy. He's gone into space a couple times, private astronaut, Jared Isaacman, and he was going to be the new NASA administrator. Well, he went through the nomination process on the Hill, testified, they grilled him up there, they kind of liked him. Everything was going fine, and about literally 3 or 4 days before he probably would have been, got the hat to run NASA, they said, we're pulling the nomination. So Mr. Isaacman has been set adrift, and a very interesting character. He's complaining about NASA now, very interesting comments from him from videos that he's making with different interviewers, and it's pretty interesting his view of what NASA's like and what he would have changed, but that's not the point. where am I? Okay, that's the guy. This is him testifying in one of the hearings there. And, okay, so he's gone. They brought in an interim NASA administrator not too long ago. And it turns out to be one of these double duty people. The guy runs the transportation department, Duffy, and he is now, anytime a plane crashes, Duffy has got to go handle all that stuff, including trying to get NASA back in some kind of operational status. Meanwhile, something like a couple thousand people are being let loose at NASA headquarters. And I'm kind of biased because I follow NASA a lot, so I'm NSF, National Science Foundation. You have a lot of other science departments that are doing things that are in duress as well in this administration. Some of it may be deserved because you get a lot of people complaining about bloated government and, you know, they're spending too much on this or that. And so, you know, it's an ongoing debate. But anyway, this guy, he's gone. And what's happened in the last few days, you got nothing but hello NASA protests. I mean, a lot of the employees of NASA are outside of NASA headquarters in Washington, D.C. with a lot of signs. This just happened a couple days ago. So, you know, I don't know where this is going to go, but it's really something to watch because in the middle of all this, there's something, you know, maybe, I don't know, 65 projects or different kinds of decisions that got to be made about keeping a spacecraft online, doing something with it, brand new programs that, you know, are being waylaid. You've got the Artemis program, which is the astronauts going back to the moon, kind of in a limbo state. There has to be some decision making going on. And it's really kind of haphazard right now, and maybe there's a lot of internal memos going on, but from the outside, it's kind of a little bit of a disaster. And not that NASA may have bloated budgets and this and that, but we'll see how this really plays out here in the next few months, because, I mean, decisions have to be made fairly soon on some key things, and I'm not sure the talent there at the top level at NASA is really fully engaged. It's like a out-of-control Star Trek ship or something. Anyway, meanwhile, the things I've been writing about recently are kind of fun. Just a few things, and I'll shut up here. But one thing that, you know, we have the Ingenuity helicopter on Mars that was an incredible test bed experiment that Perseverance, the NASA rover on Mars in Jezero Crater, let loose his helicopter. Well, that thing flew about 72 times after it was deployed, and an incredible first helicopter flight on another world. And a new proposal has just been put out of a really kind of interesting, kind of a low-cost approach, maybe. I don't know what the numbers are. But it would be 6 of these helicopters being dispatched over Mars, and they would all go to different places on Red Planet, and they would do investigations of future human landing sites. So it's kind of a cool, but again, the worst part about writing about space is I fall for the artwork. And how much these things cost in the end, and how you know, problematic they are. I'm kind of at, you know, you balance yourself when you're writing, but I love this proposal. It just shows the creative talent of how do you explore Mars, maybe on the cheap compared to where we've gone in the past. So that's one thing that just happened, you know, a couple days ago. I had a great time writing a story that's not out yet, but it's a fairly interesting thing. It's much tied to the NASA issues, and that is the private democratization of space exploration. Can we do low-cost probes out there from universities? The woman on the right is Sarah Seeger. She's at MIT, and she's holding a Venus probe. They've designed a entry vehicle that would be launched by a rocket lab booster, which is a small private entrepreneurial rocket firm, and it would explore the clouds of Venus. It has one specific experiment on it to look for organics in the upper atmosphere of Venus, and that could lead to speculation about is there life within the clouds of Venus. And I had a blast talking to her. Barb and I were on there. She took me, it was the first time in my life, and I've done a lot of interviews, she said, give me, we'll zoom in and I'm going to take you on a tour of my lab. She was so proud of her new lab. She got private money to build a whole new lab. So we walked around in her lab. It's the first time I told her I didn't have to wear goggles. I didn't have to have a bunny suit on. And, it was very safe and sane. But she took me around in the lab. She held up the probe. This is kind of a 3D printing of what the actual size of the probe is. But anyway, everything is kind of going interestingly well for her on this experiment. They got to get the thing off the ground and go onto Venus, but it could happen pretty soon. But that was a really intriguing interview. This could be a trend in the future of smaller companies doing great things at planet scale exploration. This is a weird one that came up 2 days ago. DARPA, the defense folks, have a guy that's been looking at the moon. How do you create a business on the moon? What do we do there? How do we set it up? Should we? What's the law? What's the thing? And, it's a great study of how to put in place a potential use of Earth's moon as a economic wellspring of things. And the first email I got back from somebody that hated that picture on the left, with the lights on the moon. Oh my God, we're in trouble. But who knows what that's going to be like in the future. The moon is definitely going to be a different place. It may not be by the United States, it could be by other countries, China in particular. But there was really a move on to try to understand the dynamics of the moon, the economic wherewithal, how much money it's going to cost, should we be doing it, the legal biggle stuff of who owns what property on the moon, do we have to have property on the moon, we work together, or where are we going to go? So anyway, it's ongoing. It's kind of an interesting new study that I wrote about. And then, remember just a few days ago, we had an anniversary of the first moon landing. This is, what are we talking about, 65 years now? What is it? What did I write? It's a long time ago. I lived through that thing, but we just went through a whole nother anniversary, of Neil and Buzz on the moon and the first moon landing. And, the big celebration was not this particular bunch of photos, but it was, Buzz got to talk to the Pope. The Pope called Buzz Aldrin, and Buzz is like on oxygen, and, he's getting out there. He's a good friend of mine, and we wrote a couple books together, and great guy, and he's hanging in there, and he's got a lot of opinions about the future of space exploration. But the Pope called him, on July 20th and said, let's talk about the moon and bless everybody at the same time. We also had asteroid day just a few days ago. And for those that didn't worry about it, it was no impactor coming in, but the asteroid day is meant to signify more attention to whether or not space rocks are going to come in. And what would that do to us if we had a civilization busting kind of event? And we've had some pretty interesting impacts in the past. In Chelyabinsk, Russia, a few years ago, that was a kind of an early warning sign of what an asteroid could do to a city. I did an interview with a guy, one of the leading experts. I said, well, if you were in Chelyabinsk when that asteroid came in and exploded over the whole city, what would you do? He said, well, I'd run to the window. Well, it turns out the windows blew out. So anyway, you got to be careful on these asteroid impacts, and we've got some pretty interesting close flybys at all times. We've got one that's hanging out there that people are still debating about whether or not it's not going to be an Earth impactor, but it could hit the moon. I think the last time we met here, I talked about that potential of that object hitting the moon in a few years from now. Again, it may not be a worrisome thing, but interesting that these space rocks are out there and we should take notice. Keep an eye on the next group of people going up on the suborbital tourism flight. This is Jeff Bezos and his Blue Origin suborbital rocket. You get 6 people in there, and they go up to the edge of space, and they come back down. It's not orbital, but it's suborbital. But you know, for me, one of the best things about these things, these are people kind of off the street astronauts. You know, their backgrounds are like totally different than any of the NASA astronaut crew that goes through so much training and everything. So you don't know what's going to happen when they get up there at 65, you know, out of the atmosphere, and they're clowning around up there for a while. But a lot of them come back with pretty, William Shatner, the Star Trek hero, went up on one of these suborbital flights, and it changed his life. I mean, it was I think emotionally, to look at the Earth, it's called the overview effect, but when you get up there and really look down and see how fragile the atmosphere is and all the people you know are down there, all the buzzwords, but it's pretty interesting what happens to each one of those individuals. They usually have some really compelling narratives about what they just went through. And I think it's a precursor of, you know, what maybe in the future, a lot of people are going to go buy a ticket and get up there into space, either in suborbital or into orbit. This goes much to HP's issue of orbital debris. There was a kind of an interesting, and I don't have my glasses, so I can't read what I wrote, but there's a name for this damn thing. They used it on the space station. It's made like tentacles, and it was tested by 6 or 7 of the crews on the space station, in the space station. And it's going to be flown in space in the upcoming years to actually grab a spacecraft. And it's kind of an interesting problem because, I mean, one of the issues is if it's big enough, you can go get it. But we have, like HP talked about, there's a lot of debris that's subscale, and we've got toothbrushes and camera lenses and straps and all these things going at orbital velocity, and you run into one of those, it's a day over. So, but anyway, there's a lot of experiments like this, and what was intriguing is that they actually tested this thing on the space station, within the space station, and they had multiple crews run the thing, and apparently it was successful, but you know, I don't think you know much until you really get out in free-form space. And we'll see how this idea works in the long haul. Then we have, of all things, we got, people are selling Mars meteorites. That's the biggest Mars meteorite we got here on Earth, and they sold it at one of the auction houses. And it went for, I don't know, 25 million bucks. I don't know what the cost was, but it was pretty exciting. Anyway, somebody got a piece of Mars in their apartment now. And, be careful when you go. You know. But anyway, yeah, it's like going to, I don't know, King Super and buying a big slab of meteorite. Maybe that's it. I think that's all I had.
Okay.
Without glasses, I mean, what can I do?
Any questions for Leonard?
No, God, no.
Maybe real quick, I think we should give a shout out to Voyager.
Voyager, do
You
the
know, a light
Voyager.
day away, I think, is coming up.
Yeah.
After, what, 50 years?
Yeah.
I mean, it just is remarkable that they keep with, what, like 20 lines of code, you know, whatever the JPL is doing, hats off
Yeah,
to everybody involved in that. That's, you know, I'll date myself, I can remember when, you know, high school earth science, boy, that was a big day when both of them took off. And
yeah,
that's just been remarkable to watch, so I think that's a great testimony to, you know, to NASA and space and
Yeah.
what have you.
and the memory unit on the damn thing. You know, and it's still working. But, you know, it's also got those, talk about that, you know, those kind of plaques. That thing's so far out there now, we got plaques on there, you know, in case aliens come and run into it, at least they would supposedly be able to figure out where this thing was launched from and why and all that, and it's pretty cool. But yeah, that's a big tribute to spacecraft designers, and you know, they've lost it. How many times they've lost the thing?
Right.
And they picked it up again, right? You know, so it's really unbelievable. It keeps on ticking.
I think they just refired some thrusters to
Yeah,
turn it around again that hadn't worked. and
that's great.
remarkable.
That's great. But stay tuned. There's more to come, and God knows where we're going. But it could be up, could be down.
Hey, did any Zoomers have any questions for Leonard or comments?
Clark Chapman may want to pipe in. Asteroid Man. No?
No. And John Williams, did anybody send you anything to show?
Nope. And I don't have anything either. Sorry. It's been cloudy here in Santa Fe. Last night was the first night in 40 days that I've been able to get outside.
I have a question.
Okay,
Is there anywhere where these videos, I know they're saved, is there anywhere where anyone could come look at them?
So we save them to our website, which is sky-watchers.co. And we have the whole most of the archive. Some of the meetings people didn't want to have us record, but that's where it is. And this one will be up in the next few days.
So skywatchers.com.
It's sky-watchers.co. I can send that link to you.
No, I have some interest from students who want to watch some of these programs.
Okay.
Cool. We like that.
Yeah.
All right. Well, and that's it. It's not quite dark out yet, so I don't know, John, have you made a decision?
No.
Okay. So we'll see how many people are here by the time it gets done. So let's do it. Close a wrap. And good night, Zoomers. And now let's